December 18th, 1944. A snow-covered field 3 miles east of Houffalize, Belgium. Oberleutnant Werner Schmidt crouched beside his disabled Panther, watching through Zeiss binoculars as 3 American Sherman tanks advanced across open ground at 12 miles per hour. His loader was dead, his gunner had a shattered femur, and the Panther's transmission had finally given up after 93 hours of continuous operation, seizing solid in a way that meant this 45-ton machine wasn't going anywhere without a Berger Panther recovery vehicle that wouldn't arrive for another 6 hours. But Werner wasn't thinking about evacuation. He was thinking about what he'd just witnessed. One of those advancing Shermans had fired its 76mm gun while still moving at full speed, and the round had struck a dug-in Sturmgeschütz 3 precisely in the turret ring from 800 yards. The math was impossible. Moving tanks don't hit targets at that range. Werner had spent 2 years commanding Panzers, had destroyed 14 enemy tanks across 3 campaigns, and knew with absolute certainty that what he'd just seen violated every principle of armored warfare. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The German tank doctrine was built on mathematics as reliable as gravity. A tank moving across uneven terrain at combat speed experienced constant motion. The hull pitched over bumps and depressions. The suspension compressed and rebounded. The entire vehicle rocked on its tracks like a ship in moderate seas. Mount a 9-foot gun barrel weighing 1,500 pounds to that moving platform, and physics delivered its verdict with mechanical certainty. Accuracy beyond 200 yards became a statistical impossibility. Werner had read the reports from the proving grounds at Kummersdorf. The captured American Shermans, that German engineers had tested extensively since 1943. The technical summaries noted superior automotive reliability, excellent crew ergonomics, and a gyroscopic system mounted beside the gunner that German analysts couldn't quite understand. The reports mentioned it existed. They documented its components. But they never explained what it did or how it worked, because in field testing, the captured Shermans fired while stationary. Exactly like German doctrine demanded, the Americans were supposed to be afraid of Panthers. Intelligence reports said so. Prisoner interrogations confirmed it. Every tactical engagement proved it. The Sherman's 75mm gun couldn't penetrate a Panther's frontal armor beyond 300 yards. The Sherman's glacis plate was only 51mm thick. A Panther's 75mm L70 gun could punch through that from 2,000 yards. The technical superiority was overwhelming, documented, absolute. So why was Werner's Panther burning, its ammunition cooking off in a chain reaction that would turn the fighting compartment into a blast furnace, while those 3 Shermans continued advancing, turrets traversing smoothly, guns firing, hitting targets that should have been impossible to engage while moving? The answer was inside a black box that weighed less than 300 pounds, developed by a 34-year-old Westinghouse engineer named Clinton Hanna, who'd solved a problem every military in the world had declared unsolvable. But Werner didn't know that. No German tanker knew that. And by the time German intelligence finally understood what they were facing, the war would be 3 weeks from over, and the knowledge would die in burning filing cabinets in Berlin, alongside everything else the Thousand-Year Reich had promised. Clinton Hanna received the assignment in the spring of 1939 because he specialized in precision control systems, and the United States Ordnance Department was desperate enough to try anything. The specification request was brutally simple. Develop a system to keep tank guns steady while the vehicle moves over rough terrain at speeds up to 15 miles per hour. No engineering details, no suggested approaches. Just the desired outcome and an 18-month timeline. Every major military power had studied gun stabilization. Every major military power had concluded it was theoretically possible and practically impossible. Gyroscopes existed. Naval vessels used them for fire control. Servo mechanisms existed. Aircraft autopilots relied on them. But integrating those technologies into a 32-ton fighting vehicle that would be driven by teenagers across North African deserts and European mudfields, that would be maintained by mechanics with minimal technical training, that would experience temperatures from -20 to +120 degrees Fahrenheit, that would absorb the shock of incoming fire and the recoil of outgoing fire and the constant vibration of engines and tracks? The engineering challenges weren't just difficult, they were compounding. Hanna's first prototype used 2 gyroscopes for redundancy. Summer 1940 tests at Aberdeen Proving Ground showed promise. The gun stayed within 3 degrees of elevation, while the tank moved at 12 miles per hour over moderate terrain. 3 degrees sounded precise until you calculated what it meant downrange. At 800 yards, 3 degrees of elevation error translated to 42 feet of vertical dispersion. You might hit the ground in front of the enemy tank, you might hit the sky above it, you probably wouldn't hit the tank. The breakthrough came under pressure that would have crushed most engineering programs. December 7, 1941, erased every comfortable timeline. Pearl Harbor meant production schedules that had seemed aggressive now looked dangerously slow. The M4 Sherman medium tank was scheduled to begin production in February 1942. Hanna had 8 months to deliver a stabilization system that worked, could be mass-produced, and wouldn't require a mechanical engineering degree to operate. He abandoned the 2 gyroscope approach entirely. The solution that emerged was conceptually radical, a single anticipating gyroscope that predicted gun movement before it happened, rather than reacting after the fact. Traditional stabilization worked like a man trying to balance a broom on his palm, constant small corrections chasing the problem. Hanna's system worked like a man who could see the future half a second ahead and prevent the broom from tilting in the first place. The gyroscope spun at 10,000 revolutions per minute, fast enough that its angular momentum resisted any attempt to change its orientation. Mount that gyroscope to sense the gun's elevation axis, and any upward or downward movement of the tank hull would try to tilt the gyroscope. The gyroscope would resist that tilt, generating a signal proportional to the disturbance. Feed that signal into a hydraulic servo valve, and the valve could drive a piston that pushed the gun in the opposite direction, cancelling the motion before it became visible in the gunner's sight. The entire system weighed less than 300 pounds and integrated directly with the Sherman's existing oil-gear hydraulic turret traverse system, pulling power from the same pump that rotated the turret. The elegance was in the integration. No separate power source, no redundant controls, just a black box that inserted itself between the gunner's hand control and the gun itself. When the system was engaged, the gunner still aimed normally, but the gun responded with supernatural steadiness. Aberdeen Proving Ground tests in September 1941 delivered numbers that forced even the skeptics to pause. Sherman prototype with stabilizer engaged, target at 800 yards, tank speed 12 miles per hour over rutted test course, 7 hits out of 10 shots, same tank, same crew, same course, with stabilizer disengaged, 1 hit out of 10. The difference wasn't marginal, it was categorical. Production began immediately. By August 1942, the first Sherman battalions were forming up for deployment to North Africa, and each tank carried the black box that ordnance officers had called a fantasy 18 months earlier. But there was a problem that no one had anticipated during the rush to production, a problem that wouldn't reveal itself until the hardware reached the men who had to use it. The technical manual for setup and operation was 47 pages long. The calibration process required a skilled technician and 2 hours of careful adjustment. Oil pressure had to be verified, gyroscope spin-up time had to be monitored, electrical connections had to be checked in sequence. 1 loose connection, 1 air bubble in the hydraulic line, 1 miscalibrated sensor, and the entire system would fail, or worse, fight against the gunner's commands and make aiming impossible. Most Sherman battalions forming up in the summer of 1942 didn't have a single man trained on the system beyond a cursory familiarization lecture. The crews were draftees and volunteers who'd been civilians 6 months earlier, learning to drive 32-ton vehicles and load ammunition and communicate by radio and execute fire commands and navigate by map and perform field maintenance on engines and transmissions and suspensions. Adding a complex electromechanical hydraulic stabilization system to that training burden was theoretically possible. In practice, it was one technical specialty too many for the time available. When the first Shermans rolled off transport ships in North Africa, crews looked at the unfamiliar controls beside the gunner's seat, flipped through the intimidating technical manual, and made a decision that seemed entirely reasonable. They switched the stabilizer to off and went to war the way doctrine said they should, stopping to shoot like every other tank crew in every other army. The British 8th Army received 252 M4 Shermans in the weeks before the El Alamein offensive, and their approach differed in one critical detail. Westinghouse had embedded technical representatives with British maintenance units specifically to train crews on stabilizer operation. It wasn't comprehensive training. There wasn't time. But it was direct instruction from men who understood the system's temperament. Some crews absorbed the lessons and practiced the setup until the 27 steps became automatic. Most ignored it, trusting doctrine and experience over unfamiliar technology. But a handful of tank commanders saw potential in the black box. And on October 24, 1942, that potential became lethality. British 9th Armoured Brigade advanced against German Panzer III and Panzer, 4 positions at 1,200 yards in the grey dawn light. Doctrine said, close the distance, stop, engage. But the crews with stabilizers engaged discovered something that changed the equation. They could fire while still moving forward at 8 miles per hour, and their shots landed on target. Not every shot. The stabilizer couldn't eliminate all motion, and gunner skill still mattered, but enough shots to matter tactically. German tank commanders, trained to expect the universal stop-shoot-move pattern, were caught in mid-maneuver. They'd spotted the advancing Shermans, begun their own stops, waited for their vehicles to settle, started bringing their guns to bear, and died before their gunners could center their reticles. The Shermans fired first. And in tank combat, first usually meant only. The after-action reports from German units noted abnormal accuracy from American tanks in motion, with the careful language of professional soldiers describing something they didn't understand. One captured Panzer IV crew, interviewed by British intelligence officers, stated it plainly. We stopped to fire as trained and as always works. The American gun was already aimed at us. No German tank had this capability. The Panther wouldn't enter service until mid-1943, and even then it would lack gun stabilization. The Tiger, vaunted for its 88mm gun and thick armor, traversed its turret manually when power drive failed, which it did frequently, requiring 720 full revolutions of a hand crank to rotate 360 degrees. The Americans had delivered a capability the Germans didn't know was possible, and German engineers who examined captured Shermans couldn't replicate it. The gyroscope technology existed in German industry, but integrating it into a combat vehicle that worked reliably under field conditions? That was Hanna's breakthrough, and it was harder than it looked. The brutal mathematics of El Alamein proved the concept. Sherman crews with stabilizers engaged and proper training achieved 70% hit rates at ranges from 300 to 1,200 yards, while their vehicles were still in motion. Crews without stabilizers, following conventional doctrine, 8 to 12% hit rates. The difference wasn't miraculous, it was 2 seconds. The stabilizer kept the gun on target through the deceleration phase when crews decided to stop and fire. They could squeeze the trigger the instant their vehicle halted, gun already zeroed on the enemy, no aiming delay required. German crews lost 4 to 5 seconds bringing their guns to bear after stopping, settling their sights, finding the target again. In engagements measured in heartbeats, those seconds were fatal. The United States 1st Armored Division landed in North Africa in November 1942 with over 300 Shermans, and the stabilizer sat disabled in 80% of them. The reasons were entirely logical from the perspective of tank commanders trying to keep their crews alive with minimal training time. The system was complex. Setup required precise calibration that field mechanics hadn't been trained to perform. In the Tunisian desert, sand infiltrated everything. Engines, transmissions, turret rings, and delicate electrical equipment seemed like an invitation to failure. Veteran tank officers, the men who trained the crews and would lead them into combat, cited practical concerns that sounded like wisdom. Too complicated, unreliable in these conditions, breaks too easily, and then you've got a gun that won't aim at all. the stabilizer remained installed. Removing it would have required depot-level maintenance. But the switch stayed in the off position, and the system gathered dust inside vehicles designed around it. Field Manual 17-12, Tank Gunnery, published in April 1943 after American tanks had been in combat for 6 months, included a passage that became the official excuse for every crew that disabled their stabilizer. Firing with the 75mm gun while moving is inaccurate and causes an uneconomical expenditure of ammunition. Do it only in an emergency and at ranges of 600 yards or less. The manual acknowledged the stabilizer's existence in technical diagrams, but framed fire on the move as a desperation tactic rather than a tactical advantage. Crews read that passage and concluded the Ordnance Department itself didn't trust the system enough to change doctrine. Why should they? The maintenance crisis compounded skepticism into active rejection. The stabilizer required 4 things to function: correct hydraulic oil pressure from the turret traverse pump, a gyroscope spun up to 10,000 RPM and held there, electrical power to the servo control unit, and precise calibration of the sensing mechanism that translated gyroscope signals into hydraulic commands. In depot conditions, with trained technicians, setup was methodical. In field conditions with mechanics who'd received a half-day familiarization course, setup was guesswork. One air bubble in the hydraulic line caused erratic gun movement. One corroded electrical connection made the servo fight against the gunner's commands. One improperly calibrated sensor caused the gun to hunt, oscillating up and down in search of stability it couldn't find. When crews tried the stabilizer and experienced these failures, word spread through tank battalions with the speed of survival information. The stabilizer's junk. Turn it off before it gets you killed. No one blamed the inadequate training or the rushed maintenance procedures. They blamed the technology. The deadly consequences revealed themselves at Kasserine Pass in February 1943, where American armor met German Panzer forces in the first major engagement between the two armies. 183 American tanks were destroyed over 4 days of fighting. The tactical failures were numerous: poor coordination between units, inadequate reconnaissance, defensive positions chosen without regard for fields of fire. But the technical failure was invisible because no one knew it existed. American Shermans with stabilizers disabled followed stop doctrine against German tanks using the same doctrine. The engagements came down to crew training, tactical positioning, and weapon performance. In those categories, experienced German crews with superior optics and longer-range guns held the advantage. German after-action reports praised the mechanical reliability of captured American tanks and noted their excellent ergonomics, but concluded, enemy crews stopped firing as expected. Standard engagement protocols remain effective. The Americans had brought a secret weapon to the battlefield and never unwrapped it. The turning point came not from high-level tactical analysis, but from individual curiosity and obsessive preparation. Lieutenant Joseph McCoy, 26th Tank Battalion, 66th Armored Regiment, 2nd Armored Division, spent the Atlantic crossing to Sicily, reading the Westinghouse Technical Manual cover to cover. Not skimming it, reading it. He worked through the calibration procedures on paper, memorizing the sequence. He studied the troubleshooting charts until he could diagnose failures by symptom. Other platoon leaders ran poker games or slept or wrote letters home. McCoy drilled his crew on stabilizer setup until the 27 steps became automatic. Verify oil pressure gauge reads 180 to 220 psi. Engage master power switch. Wait for the gyro spin-up indicator. Check servo response with test displacement. Calibrate 0 point with gun level. Engage stabilizer clutch. Verify the gun holds position during simulated motion. His gunner could perform the sequence in under 10 minutes without consulting the manual. Other platoon leaders mocked him quietly. McCoy's wasting time on that contraption. Wait till the first breakdown, then we'll see. The Geller beachhead, on July 10, 1943, provided the laboratory. German Panzer IV tanks counterattacked the Allied landing zones in the kind of mobile engagement that doctrine said favored the defender. German crews knew the terrain, had prepared positions, and could use maneuver to offset numerical disadvantage. McCoy's platoon advanced with stabilizers engaged, and he briefed his crews on something the British had learned at El Alamein. You didn't fire on the move for accuracy at long range. You fired on the move for two reasons: suppression and preparation. Suppressive fire kept German crews buttoned up, reluctant to expose themselves to spot accurately. It degraded their ability to coordinate and maneuver. It wasn't about hitting them at 800 yards while moving. It was about forcing them to respect your fire while you closed the distance. And when you reached 600 yards and made the decision to stop and deliver a killing shot, your gun was already on target. No aiming delay. Crosshairs exactly where you'd left them. Squeeze trigger. Absorb recoil. Fire again if needed. The German crews went through their practice sequence. Stop vehicle. Wait for settling. Center sight picture. Acquire target. Aim. Fire. By the time they completed that sequence, McCoy's gunner had already put a round into their hull. The word traveled through the 2nd Armored Division like electricity. Crews who mastered the stabilizer gained 3 to 4 critical seconds in every engagement. It wasn't about revolutionary tactics or dramatic battlefield miracles. It was about cutting aiming time to 0 when you stopped. The gyroscope held the crosshairs exactly where the gunner had placed them 30 seconds earlier, before the tank started moving, before terrain intervened, before anything changed. Stop the tank and the gun was ready. No searching for target. No compensation for movement. Just fire. The United States Army Ordnance Department, stung by Kasserine and confused by mixed field reports, conducted formal testing at Fort Knox in the summer of 1943 with controlled conditions and instrumented measurements. The results were published as technical bulletins that reached every armored unit. Stabilizer-equipped crews with proper training reduced time to first shot by an average of 4.2 seconds compared to non-stabilized tanks. Hit probability at 800 yards increased from 45% to 68% for stabilizer-trained crews under controlled test conditions. In combat, where stress and chaos degraded performance, the advantage was less dramatic but still measurable. Properly trained crews averaged 55 to 60% hit rates versus 30 to 40% for conventional crews. The data forced a quiet revision of doctrine. The next printing of Field Manual 17-12 would include updated guidance on stabilizer employment. But thousands of tank crews were already in combat, and changing doctrine in headquarters didn't change what men believed in the field. The stabilizer's reputation had been established by early failures and inadequate training. Recovering from that reputation required proof delivered in blood and survival. The Normandy bocage country revealed the stabilizer's value in terrain that doctrine manuals hadn't anticipated. The hedgerows of northern France, thick earthen berms crowned with centuries-old vegetation creating natural walls between tiny fields, turned tank combat into knife fights at ranges under 300 yards. Visibility was measured in vehicle lengths. Engagement windows lasted seconds. German crews dug into prepared positions with clear fields of fire down narrow lanes, held every advantage of position and preparation. American Sherman crews advancing through the bocage needed every technical edge they could find. And by June 1944, enough crews had been trained on stabilizer employment that the system finally reached its intended battlefield role. The application was brutally practical. When a Sherman took fire and had to reverse rapidly out of a killing zone, the violent rocking motion from backing over uneven terrain at speed normally made aimed fire impossible. Crews with stabilizers engaged could shoot while rocking backward, the gyroscope keeping the gun steady through motion that would have thrown off any manual aim. Crews reported the effect with the matter-of-fact language of men describing tools that kept them alive. We can get 2 aimed shots off while reversing before the German tank can fire once. That's the difference between making it back to cover or burning in the lane. The stabilizer didn't eliminate danger. Nothing could in terrain that favored the defender so completely, but it compressed the window of vulnerability from lethal to survivable. The compound advantage of American tank design became clear in these close-range engagements, where multiple technical factors combined to create tactical superiority. Sherman turrets rotated 360 degrees in 15 seconds using electric-hydraulic power traverse. 20 degrees per second of smooth, controlled rotation. A gunner could track a moving target continuously, the turret keeping pace with threat movement while the stabilizer kept the gun steady in elevation. German Panther tanks, vaunted for their sloped armor and powerful 75mm L-70 gun, rotated their turrets in 18 seconds at high speed. But the power traverse system was notoriously unreliable, prone to failure from combat damage or mechanical breakdown. When power traverse failed, Panther crews resorted to hand-cranking the turret at 0.36 degrees per revolution, 720 complete revolutions to traverse 360 degrees. In close combat, where targets appeared suddenly and disappeared quickly, a Panther with failed power traverse was a pillbox with excellent armor and a gun that couldn't track. The German Tiger I, the heavy tank that dominated Allied nightmares and German propaganda, required 60 seconds for full turret rotation at low engine RPM. The hydraulic system drew power directly from the engine, so traverse speed depended on engine speed, and idling Tigers traversed at glacial pace. American crews learned to exploit this, force the Tiger to traverse, then move laterally faster than its turret could follow. The Sherman's 20 degree per second traverse rate meant American gunners could stay on target, while German crews struggled to keep up. Add the stabilizer to that equation, gun steady during the Sherman's movement, ready to fire the instant the crew chose, and the technical advantages compounded into tactical dominance in exactly the kind of close-range, high-speed engagements the bocage demanded. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The revelations spread through armored units as crews compared notes and survival rates. Stabilizer-trained platoons reported consistently higher kill ratios and lower casualty rates than conventional platoons, in the same battalion facing the same opposition. The data was anecdotal but compelling. Crews who trusted the system lived longer, even when German guns were superior, and the Panther's 75mm L-70 could penetrate Sherman frontal armor at ranges beyond 1,500 yards. American crews often fired first because they arrived at firing solutions faster. The stabilizer kept the gun on target during approach. The power traverse tracked threat bearing. The gunner squeezed the trigger when geometry favored penetration, and the German crew was still bringing their gun to bear when the American round arrived. German tank crews, interviewed after capture, expressed consistent frustration with American fire control that they couldn't explain through conventional analysis. American tank turret control allows rapid engagement, one Panther commander stated in a detailed interrogation report. Crews demonstrate the ability to fire accurately with minimal halt time. We must assume the first shot advantage belongs to the enemy. German engineers studied captured Shermans, photographed the stabilizer components, measured the gyroscope, traced the hydraulic lines, and reached a conclusion that vindicated Hanna's 18 months of obsessive engineering. The system was too complex for field production in Germany's increasingly strained industrial system. The gyroscope required precision manufacturing. The servo control unit needed specialized electrical components. The integration with hydraulic systems demanded careful calibration. Germany could build the components, barely, but couldn't manufacture them at scale, with the reliability needed for combat vehicles. The stabilizer required an industrial base that could produce precision instruments by the thousands, and assumed they'd work correctly, without individual tuning. Germany's artisan approach to tank production, where every vehicle received individual attention and adjustment, couldn't replicate the mass production precision the American system assumed as baseline. A captured German technical manual from Panther crews, dated August 1944, included tactical guidance that acknowledged defeat without understanding its source. American tank turret control allows rapid engagement. Crews demonstrate the ability to fire accurately with minimal halt time. Assume the first shot advantage belongs to the enemy. Compensate through superior positioning and use of terrain. The Germans had adapted their tactics to counter an advantage they couldn't match technically, falling back on the traditional Panzer virtues of crew skill and tactical placement. It was sound doctrine against a superior system, but it conceded the initiative. By September 1944, American Sherman production reached 1,200 tanks per month, and every vehicle rolled off the assembly line with the Westinghouse stabilizer installed as standard equipment. The setup procedures had been simplified through field feedback and engineering refinement. What took 12 hours of technician time in 1942 now took 4 hours of crew time in 1944. Training courses at Fort Knox dedicated entire days to stabilizer employment, with instructors who'd survived combat explaining the system not as complicated technology, but as life-saving equipment. Crew training rates climbed from 15% in 1943 to 60% by autumn 1944. Hit rates for stabilizer-trained crews peaked at 72%, at combat ranges of 300 to 1,000 yards in good visibility, with trained gunners and properly maintained systems. The Edge Clinton Hanna had built in a Westinghouse laboratory was now standard equipment in the most produced tank of the war, integrated so completely that crews treated it as normal rather than revolutionary. The stabilizer's golden age lasted from D-Day through the autumn of 1944, when American armor faced German tanks that were individually superior but collectively overwhelmed by numbers, logistics, and integrated technical advantages that compounded into battlefield dominance. The Sherman wasn't invincible. Far from it. But it was fast, reliable, and in the hands of properly trained crews, lethal at the ranges where most tank combat actually occurred. The mathematics that had seemed impossible in 1939 were now routine. Fire while moving, hit while moving, survive while moving. The M4A3E8 Sherman, nicknamed the Easy 8, represented the culmination of everything the United States had learned about tank design through 3 years of combat. First introduced in December 1944, just in time for the Battle of the Bulge, the Easy 8 combined the 76mm high-velocity gun, improved horizontal volute spring suspension with wider tracks, welded hull construction, and the refined second-generation Westinghouse stabilizer that had been simplified and improved based on combat feedback. The Easy 8's stabilizer was easier to maintain, faster to calibrate, and more resistant to the kind of field damage that had plagued earlier versions. The system could now be set up by a trained crew in under 30 minutes without specialized tools. The gyroscope housing was sealed against dust and moisture, the hydraulic lines were reinforced, the electrical connections were waterproofed. Every failure point identified through 3 years of combat use had been addressed. Oberleutnant Werner Schmidt had been fighting American Shermans since Tunisia in 1943. He'd destroyed his first Sherman at Kasserine Pass, a clean kill at 1,100 yards that validated everything his instructors at the Panzer School had taught him about the superiority of German gunnery and German armor. He'd watched American tanks burn at Salerno, at Anzio, across the Gustav Line. The Americans had numbers, they had industrial capacity, but they didn't have technical sophistication. That's what the intelligence briefing said. That's what every captured Sherman examination confirmed. The Americans built simple, reliable machines operated by adequately trained crews who compensated for technical inferiority through numerical superiority and aggressive tactics. It was a sound assessment based on solid evidence, and it had been accurate for 2 years. Then Werner encountered his first Easy 8 on December 18, 1944, and everything he knew stopped making sense. The engagement started conventionally. Werner's Panther was positioned in defilade behind a stone farm wall, covering a crossroads where American armor had to advance if they wanted to push toward Hofelize. Visibility was good. The range to the crossroads was 800 yards. The Panther's 75mm L-70 could penetrate any Sherman at that range with contemptuous ease. 3 Shermans appeared, advancing in a wedge formation at 12 miles per hour. Werner gave the fire command. His gunner, a veteran from the Eastern Front named Klaus, centered the reticle on the lead Sherman's glacis plate and fired. The round struck dead center and bounced off. Werner blinked, recalculated. The angle was wrong. The Sherman must have been oriented differently than he'd estimated. "Reload," he ordered. "Target, lead tank. Compensate 2 miles right." Klaus fired again. This time the round struck the Sherman's turret front and ricocheted into the sky. Werner heard his loader's voice, higher than normal. "Herr Oberleutnant, that's not a..." Normal Sherman. The turret shape is different. The suspension is different. Werner raised his binoculars. The loader was right. These Shermans had wider tracks, different road wheels, and something about the turret that suggested additional armor or a different casting process. But before Werner could process that information, all three Shermans fired. While still moving, at 800 yards, the first round struck the ground 30 yards short, the second round whistled overhead. The third round hit the stone wall directly in front of Werner's position, showering the Panther with rock fragments and dust. The Americans were firing on the move. That shouldn't be accurate enough to matter. Werner traversed left, seeking a flanking shot. His Panther's Maybach engine roared. The turret slewed smoothly on its power drive. Klaus acquired the target, centered the reticle, fired. The round hit. Werner saw the impact flash on the Sherman's side armor. But the Sherman didn't stop. Didn't burn. Didn't even slow down. The Americans were using the new 76mm gun. Werner had read the intelligence briefs. Superior penetration compared to the old 75mm, still inferior to the Panther's gun, but closer. More dangerous at medium range. The three Shermans split up. One continued straight toward the crossroads. The other two broke left and right, executing a flanking maneuver that was textbook American tactics. Aggressive, simple, effective if you had enough tanks to absorb the losses. Werner ordered his driver to reposition. The Panther backed away from the stone wall, seeking new cover behind a farmhouse 50 yards to the rear. Standard German tactic: engage from concealment, fire, displace before return fire arrives, never stay in one position long enough to become predictable. The Panther's transmission made a grinding sound, then a clunk, then nothing. Werner felt the tank coast to a stop. The engine was still running, but the power wasn't reaching the tracks. The final drive had failed, just like the maintenance reports said it would after 90 hours of continuous operation. The Panther was now a stationary gun platform with excellent armor and no mobility. Werner keyed his radio. Adler 3 to Adler lead. Transmission failure. Require recovery vehicle. Current position. The first 76mm round hit the Panther's turret side. The impact sounded like a church bell struck with a sledgehammer. Werner's ears rang. The interior was filled with metal fragments and the smell of scorched steel. Klaus screamed. Werner looked down and saw his gunner clutching his leg, blood pumping between his fingers. The loader was slumped against the ammunition racks, his face grey, his chest not moving. Werner grabbed Klaus under the arms and dragged him toward the turret hatch. A second round hit the Panther's engine deck. This time Werner heard the secondary explosion as fuel lines ruptured. Black smoke began pouring into the fighting compartment. Werner shoved Klaus through the hatch, climbed out after him, and dropped to the ground beside the burning Panther. He looked across the field. The three Shermans had stopped now. 800 yards away, turrets traversed in his direction. But they hadn't fired again. The Americans didn't waste ammunition on tanks that were already dead. Werner pulled Klaus behind cover and applied a tourniquet to the shattered femur while smoke from his Panther rose into the December sky. And Werner thought about what he'd seen. Those Shermans had fired accurately while moving at 12 miles per hour. Not one lucky shot, multiple shots, enough to make him think they could see where their rounds were going, enough to make him think they had some way of keeping their guns steady that German tanks didn't have, enough to make him question every intelligence briefing he'd received about American technical inferiority. 3 days later, Werner was in a field hospital near Prüm, waiting for evacuation to a rear area facility where doctors would determine if Klaus's leg could be saved. A Hauptmann from the Army Weapons Office arrived, carrying a briefcase and looking for tank commanders who'd engaged the new American Sherman variant. Werner described the encounter. Hauptmann took notes, asked detailed questions, and finally showed Werner a photograph. "This is what you fought," Hauptmann said. "The Americans call it the M4A3E8. We're calling it the Sherman Easy 8. It has the 76mm gun, improved suspension, and something our engineers are still trying to understand fully. A gyroscopic stabilization system that allows accurate fire while the tank is in motion." Werner stared at the photograph. That's impossible. Moving tanks can't hit targets at combat ranges. Hauptmann's expression suggested he'd heard this before. That's what we thought. That's what every principle of gunnery says. But the Americans have found a way. Our engineers examined captured Shermans in 1943 and found the gyroscope assembly. They couldn't replicate it. The precision manufacturing required exceeds our current industrial capacity. So the Americans have been able to do this since 1943? Werner asked. Hauptmann shook his head. The system has existed since 1942, but American crews didn't use it. Training was inadequate. Maintenance was too complex. Most crews disabled the stabilizer and fought conventionally. That's why we didn't understand what we were facing. When we tested captured Shermans, we tested them the way American crews were actually using them. Stabilizer, off, fire while stationary. But now they're using it, Werner said. Now they're using it, Hauptmann confirmed. Training has improved, the system has been simplified, and the EZ-8 has a refined version that's even more reliable. The Americans have turned their tanks into mobile gun platforms that can shoot accurately at speeds that make them very difficult to hit. Combined with their numerical superiority and logistical advantages, this creates a tactical problem we don't have a good solution for. Werner thought about his Panther, burning in a Belgian field. He thought about Klaus, who would probably lose his leg. He thought about the loader whose name he couldn't remember, who died before Werner could drag him from the tank. He thought about 2 years of fighting Americans who'd seemed afraid of German armor, who'd relied on numbers rather than quality, who'd validated every assumption about Teutonic technical superiority. How many of these EZ-8s do they have? Werner asked. We estimate around 2,000 produced so far, Hauptmann said. Production is accelerating. By spring, most American armored divisions will be equipped with them. 2,000. Werner did the math. Germany was producing perhaps 50 Panthers per month, when the factories weren't being bombed, when the rail lines weren't being interrupted, when raw materials could still reach the assembly plants. The Americans were outproducing Germany by orders of magnitude, and now they had technical advantages that German industry couldn't match. What do we tell the crews? Werner asked. How do we fight these tanks? Hauptmann closed his briefcase. We tell them to use terrain, use concealment, engage from prepared positions at maximum range, aim for the tracks to immobilize them, then maneuver for side shots. And we tell them that American crews can fire accurately while moving, so they should expect to be under fire from the moment they're detected. That's not tactics, Werner said. That's survival advice. Yes, Hauptmann agreed. That's exactly what it is. The reality of what the Americans had achieved spread through German armored units with the slow, grinding inevitability of bad news that couldn't be denied. Panzer commanders who'd spent 2 years treating Shermans as inferior targets suddenly found themselves dealing with a weapon system that negated Germany's carefully cultivated advantages in gunnery and crew training. The gyroscopic stabilizer didn't make the Sherman invincible. The EZ-8's frontal armor was still vulnerable to the Panther's gun at any combat range. The 76mm gun still couldn't reliably penetrate a Panther's frontal glacis beyond 600 yards. But the stabilizer changed the fundamental equation of tank combat in ways that mathematical analysis struggled to capture. A Panther that had to stop to aim accurately became predictable. A Sherman that could fire while moving remained unpredictable. A German crew that needed 4 to 5 seconds to settle their sights after stopping faced an American crew that could fire the instant they chose, with their gun already on target. The technical superiority that German intelligence had documented so carefully in 1943 mattered less than the tactical flexibility that American crews had finally learned to exploit. Staff Sergeant Jake Hartwell, 4th Armored Division, wrote home to his wife in Ohio on January 3, 1945, with the careful language of a man who knew censors would read his letter before it left Europe. We got new tanks in December, Jake wrote. Better suspension, bigger gun, and that system the instructors told us about back at Knox that nobody believed would work. Turns out it works pretty well. Makes a difference when you can keep your gun on target while you're moving. Doesn't make us bulletproof, but it helps. What Jake didn't write, because the censors wouldn't allow it, was that his platoon had engaged 6 Panthers between December 16th and December 28th and destroyed 4 of them without losing a single Sherman. What he didn't write was that the stabilizer had saved his life on December 23rd, when a Panther appeared from behind a farm building at 400 yards, and Jake's gunner put 2 rounds into its side armor before the German crew could traverse their turret. What he didn't write was that he'd stopped being afraid of Panthers, and that felt dangerous because fear kept you careful, and careful kept you alive. The Battle of the Bulge marked the Easy-8's baptism by fire, and the performance data that filtered back to the Ordnance Department validated 3 years of patient development. Stabilizer-equipped Easy-8s achieved first-shot hit rates of 78% at ranges under 800 yards when crews had been properly trained and systems were properly maintained. That was 40% higher than conventional Shermans and nearly 60% higher than German tanks that had to stop to shoot accurately. The German counteroffensive that Hitler had promised would split the Allied armies and recapture Antwerp ground down in the Ardennes mud under the weight of American industrial production and technical advantages that German staff officers hadn't anticipated. The Americans could replace losses faster than Germany could inflict them. American logistics could keep tanks fueled and armed in conditions that would have paralyzed German supply lines. And now American tanks could shoot accurately while moving, which meant German ambush tactics that had worked since 1943 suddenly produced acceptable results for the Germans, but not the decisive victories they needed. By late January 1945, German intelligence officers were writing situation reports that read like obituaries for the Panzerwaffe. Enemy armor demonstrates tactical flexibility through technical systems we cannot replicate, one report from 5th Panzer Army noted. American tank crews exploit gyroscopic stabilization to maintain fire superiority during maneuver. Our crews must stop to fire accurately. This concedes initiative to the enemy. Recommend defensive tactics, emphasizing terrain and concealment to offset American technical advantages. The recommendations were sound. They were also desperate. Defensive tactics could slow the American advance. They couldn't stop it. Not when the Americans had 73,000 tanks produced over the course of the war, supported by logistics that could deliver spare parts and ammunition to forward units within 24 hours, backed by air superiority that made daylight movement suicidal for German armor. The gyroscopic stabilizer was one technical advantage among many, but it was the advantage that German engineers photographed and measured and studied and couldn't reproduce. The Panther had superior armor and a superior gun. The Tiger had psychological impact and killing power that made Allied tankers check their escape hatches before every mission. But neither German tank could fire accurately while moving, and that single capability changed the tactical mathematics in ways that armor, thickness, and gun penetration couldn't compensate for. Clinton Hanna never knew the full impact of his work. He received technical reports from the Ordnance Department detailing hit rate improvements and maintenance statistics, but he never stood beside a Sherman in the Ardennes or watched American crews exploit the system he'd built to survive encounters with tanks that outclassed them on paper. He never met Jake Hartwell or any of the thousands of tank commanders who learned to trust the black box beside the gunner's seat. In April 1945, as American armor drove deeper into Germany, Hanna received a letter from the Army Ordnance Department. The language was bureaucratic, the tone professional, but the message was clear. The gyroscopic stabilizer had proven invaluable in combat operations. Crew acceptance had increased substantially following enhanced training programs. System reliability under field conditions had exceeded initial expectations. The letter recommended continued development for post-war armored vehicle programs. Hanna filed the letter in his desk drawer and went back to work on post-war projects that would never carry the same urgency. The stabilizer had done what the specification requested. It had kept tank guns steady while vehicles moved over rough terrain at speeds up to 15 miles per hour. That the system had been ignored for 2 years. That training failures had nearly doomed it. That thousands of tank crews had fought and died without ever using the equipment that might have saved them. None of that diminished the engineering achievement. He'd solved the problem everyone said was impossible. Eventually, the people who needed it most learned to trust it. That would have to be enough. The war in Europe ended on May 8, 1945. By then, roughly 60% of American tank crews had been trained on stabilizer employment. Hit rates for those crews averaged 65 to 70% at combat ranges, compared to 35 to 40% for crews who fought conventionally. The difference represented thousands of engagements, where American tanks fired first, hit first, and survived encounters with German armor that should have killed them. The mathematical advantage was measurable. The human cost was incalculable. German tank crews who survived the war and were interviewed by Allied intelligence officers expressed consistent themes. American tanks had become increasingly difficult to engage effectively. American crews demonstrated fire control capabilities that German doctrine couldn't counter. American armor had evolved from a numerical threat into a technical threat that neutralized Germany's advantages in crew training and vehicle performance. "We adapted our tactics," one Panther commander explained through a translator in June 1945. "We used the terrain more carefully. We engaged at longer ranges, where American guns were less effective. We assumed they would fire first and planned accordingly. But adaptation is defensive. We were responding to their advantages instead of exploiting our own. That is the definition of losing." The gyroscopic stabilizer didn't win the war. No single technology wins wars. Wars are won by the patient application of multiple advantages until the enemy runs out of counters, runs out of resources, runs out of time. But the stabilizer represented something more important than tactical advantage. It represented American industrial capacity to solve complex engineering problems at scale, to manufacture precision instruments by the thousands, to train crews on systems that required technical understanding rather than just mechanical skill. Germany could build excellent tanks in small numbers with artisan precision. America could build adequate tanks in vast numbers with mechanical consistency. When America's adequate tanks gained technical advantages that Germany couldn't match, the equation stopped being about which tank was better on paper and started being about which nation could sustain industrial production while teaching 19-year-old farm boys to operate gyroscopic stabilizers under fire. The EZ-8 went on to fight in Korea, where it faced 34 85s that were technically comparable but lacked the stabilization system that American crews had finally learned to use effectively. The stabilizer's advantage remained decisive. American tank crews achieved first-shot kills at ranges and speeds that Soviet-trained crews couldn't match. The technology that had been ignored in 1942, rejected in 1943, and grudgingly accepted in 1944 became standard equipment that new tank crews assumed had always existed. By the time the M60 pattern entered service in 1960, gun stabilization was no longer revolutionary. It was expected. The two-axis stabilization systems that kept both elevation and traverse steady became baseline requirements for main battle tanks. The digital fire control systems that calculated lead, compensated for barrel wear, and adjusted for wind became standard equipment. All of it traced back to Clinton Hanna's black box that weighed less than 300 pounds and solved a problem that everyone said was impossible. Werner Schmidt survived the war. Klaus lost his leg but survived as well, returning to Bavaria to work in the same farm his family had worked for 3 generations. The Hauptmann from the Army Weapons Office disappeared into the Soviet zone and was never heard from again. Werner's Panther remained in the Belgian field, where it burned until a French salvage crew cut it up for scrap in 1947. Werner returned to his family estate outside Potsdam, which was now in the Soviet occupation zone, and discovered that 2 years of Russian administration had destroyed more than the Americans had bombed. He moved west, to Hamburg, where he worked in his brother-in-law's machine shop and never talked about the war, except when other veterans gathered, and the conversation inevitably turned to tanks and tactics and the question of how Germany had lost when everyone knew German armor was superior. Werner never told those stories because the answer was more complicated than technical specifications and armor thickness. The answer was that American tanks had learned to shoot while moving, and German tanks hadn't, and that single capability had cascaded into tactical advantages that negated every measurable superiority the Panther possessed. The answer was that American industry could produce precision gyroscopes by the thousands, while German industry struggled to produce Panthers by the dozens. The answer was that technical sophistication without industrial capacity meant nothing when your opponent had both. Jake Hartwell returned to Ohio in August 1945, married his high school sweetheart, and worked in a steel mill for 37 years. He kept his tanker jacket in a closet and his memories in compartments he didn't open very often. When his grandson asked him about the war in 1982, Jake talked about the Easy 8 with the pride of a man who'd survived because his equipment worked when it mattered. "We had this system," Jake said, "called a gyroscopic stabilizer. Kept the gun steady while we were moving. Made all the difference when you needed to shoot first." His grandson asked if that made the Sherman better than German tanks. Jake thought about Panthers burning in Belgian fields and friends who hadn't come home, and the mathematics of survival that came down to 2 seconds of advantage in a fight that lasted 30 seconds from first shot to final death. "Better," Jake said. "I don't know any better, but it kept us alive when we needed it most. That's what mattered." Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.